So let us look at some worked examples, as in regard with pure substances. So this is example one, and the question goes: determine the specific volume of refrigerant 134A at 1 megapascals and 50 degrees Celsius using A. Ideal gas equation, B. The generalized compressibility chart. Compare the values obtained with the actual value of 0.02171 meter cubed per kilogram. Once you see meters cubed per kilogram, anytime you see a property is being struck with kilogram, you know, talking about a specific property. So this is specific volume. So we're going to be looking at specific volume. So one thing you need to notice and recognize before you attempt anything is this here, the arrow 134. Okay, wait a minute. Get some. So one thing you need to notice is this here. Once you see that, and you have to also notice, yeah, that's the first thing you have to recognize. You're giving your crew and answering it. So why am I saying that? Because that 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 element is given on the is part of the tables, you know, is part of the property tables. And before you go to answer any question, you will need these tables. So that our 134A is here on. I said the table for you is right here. Right here, you see, our 134A. So its properties are given right here. So, and the properties we really need for this answer is the critical point properties, here. That's 374.2, 4.059, and 0.1993. The specific volume and the pressure and the temperature. There's critical point properties. So what else would you want to notice? Just like any approach to any question, whenever the given quantities, you just bring them out. And yeah, so telling us part A, we use the ideal gas equation. And I hope everybody is familiar with the ideal gas equation. So to simplify that, the ideal gas equation is such that it's something that relates pressure, volume with temperature, the number of moles, and the gas constant. So anytime you see something that is trying to do with that relation, just know that's the ideal gas equation. So, and this will be table one. So that's the value. Well, in the exam, you don't have to insert the table. I was just deciding it for you to guide you on how to use it. So that's in table one. Now we're going to extract the information that we have. So you see R is equal to 0.08149. Where did we get that? This is the ideal gas equation. You see we're using pressure, specific volume with the gas constant and the temperature. But in this case, since I've said that specific volume of R134A, so within the ideal gas equation, what we try to substitute the R, we take up this value right here. You see, we get it from the table. So you're not going to answer this question without this table. So and that lies under the gas constant R, kilojoule per kilogram per Kelvin. So that's what we have right here. And so now this is the ideal gas equation, P. And one thing you have to notice, this is not volume. This is specific volume. It's volume per unit mass. Okay, that's why we have this kilogram. So, and they told us to determine the specific volume. So it's what we have and what we need. We have the gas constant given in the table. We have the temperature given in the question. It's right here in the question, 50 degrees Celsius. And we have to convert the Kelvin by adding 273. And we have pressure as 1 megapascals. So once you divide using your calculator, you should be able to get 0.02632127. So you have to notice that I've really written like everything, all the digits that came on my calculator. Why? You know, sometimes if you're not sure how many decimal points you should write, it's advisable that you just write everything that came on your calculator because you might round off and you over round off and it affects your last value. So it's wise to just write all the decimal places and you can round off on the very last answer. So part this question is telling us to compare whatever value we get with this one here. So we got 0.026 and this one is 0.021. So once you're going how are you going to compare? You're going to compare as in finding the error, you know. So you're going to get the difference, biggest minus the smallest. Okay, that is the calculated value minus the actual value, which was given in the question. And now you're going to find the percentage error, which is equal to the value. This difference here will give you something like 4.127. So you can redo it. You can redo the example and you see whether we're following wrong. So, and you divide by the actual value, you multiply by 100%, and you're going to get a percentage error of 21.24%. So you have compared the values. You could maybe make a conclusive statement and be like, from the comparison, we get a, a 1.4 percentage error. So now let's go to part B. And part B is a critical one. You see, part B, they said we should use the generalized compressibility chart. So now there is a critical part, okay? So in order to use the generalized compressibility chart, you have to have two things. You have to have the critical properties and the reduced properties. So the critical properties, I already showed them to you. They are right here on the first page on table A1. You have this point properties, and which exactly you're going to use. You're going to look at the properties there in front of the element they gave you in the question. And for this point, we have R134A, and its critical properties are temperature, pressure, and volume. So they're here. You're going to just copy them, which is 3.42 Kelvin, 4.059 megapascals, and 0.1993 meters cubed per kilogram per mole, you know. And you'll write them, you see, all of them right here. These are critical properties. So after extracting your critical properties from the table A1, now you're going to find the reduced properties, which is equal to property divided by its critical value. So in this point, hold up, get my calculator. So from from the question, we were given temperature as we were given temperature as Hold up. We was given temperature as okay, yeah. To find the critical properties, we're going to divide, to get the reduced properties. So for temperature, we was given we converted to kelvins, and now we have to divide, which is 323 divided by 3 374.2, which gives us 4.8631747772. And the critically reduced properties, they don't have units because you're literally dividing temperature with the critical temperature. So you're dividing temperature with temperature, and the Kelvin going to cancel. So now we're going to get the value of the reduced pressure, and we have our pressure as 1 megapascals. So 1 megapascals divided by 4.05 megapascals, we get 0.2469138. Do we have that? Oh, we don't have that. Why? Oh, we have it right here, yeah. 661. Oh, hold up. One. Oh, yeah. This one is too reduced. This is not real for like, let's check the critical. There's a 9. The pressure is 4.0059, okay? And you see, this is a mistake. We forgot a 9 here, and it was going to affect your last answer. So, yeah. So 1 divided by 4.059. Yes. Yeah, you're right. You get this. You get 0.2463661 as the pressure. And the critical volume, you go through the same process. You divide the ideal, which was given as there was volume, critical volume, which is the actual value is 0.0217 2117. So I'm saying it's 0.02171 divided by the, the, the critical point property, which is 0.1993, and you get 0.08931259. Yeah. So now, after getting the reduced properties, we're going to now go straight to the compressibility chart for the refrigerant 134A. Yeah. So why did we first have to look for the reduced properties? We had to first look for the reduced properties because from the compressibility chart, it's plotted against the compressibility factor Z and the reduced property as in pressure. So you cannot use this chart without having reduced pressure and the compressibility factor. So you have to note that. Okay. So, but we have a problem again. I have a problem. Do you have a problem? No, not yet. We don't have a problem yet. One thing you have to put in mind is for this refrigerant at most temperatures, okay, practical pressures, its compressibility factor Z lies between 0.8 and 0.9. So even before you use your chart, you should be able to know what value you anticipate. The value you want is going to lie from right here. It's going to lie from sorry for that. Ah, doing wrong. The value is going to lie from here to here, okay, it should lie in between these two. So now we have reduced properties, but you have to realize that this is the pressure is given along this, and the temperature is given within the chart. Yeah, and the specific volume, you won't need it here. And your chart also giving you your guide. If I can zoom out, sorry. You can see from the chart that is giving you here. You see, reduced pressure is going to pressure divided by critical pressure, temperature. Okay, we went through that. I was just showing you. Once you have your table, you can get through the formula. It's right there. You can cross check and avoid making mistakes because you have the guide. So what are we going to do here? Our reduced pressure is 0.246361. So you're going to look for that value on the chart. So once you come on the chart, reduced pressure is lies on here, and 0.246361 is approximately here, around box 8. How do we find that? So 10 boxes here represent 0.5. 10 boxes. So you have to use that logic. If 10 boxes from here to here is 0.5, that means one box is 0.05, 0.05. So to get that value, you are going to have you're going to multiply 0.05 with test number of boxes until you get a value that is approximately equal to 0.2463661. So we're going to multiply. Let's say you get the value of one box, multiply it by a number of boxes. So let's multiply by 6. So by 6 we get 0.3. I want you to go with me through this step because it's critical, it's crucial. So 6 does not work. We go to something lower, maybe 5. Yes, and with 5 we get 0.25, and it's slightly above 0.246. And actually, if you were to round off 0.246333661, you're going to get 0.05. So you're going to look for the fifth box, which is 1, 2, 3, 4, somewhere in the middle there. And after getting the box, so you mark the value of the critical pressure. Let me use which one? Let me use yellow. So you're going to you mark. I think it's 1, 2, 3, 4, 5, somewhere here. So you're going to mark that value. Now that's your critical pressure, and you want to put a straight ruler and you mark the value until you hit the temperature curve. You see these these there are graphs that are plotted at different temperatures. So you have to look for the temperature you want. And we got a critical temperature of 0.0863174772. So that's approximately 1. And we see 1 is here. The graph is it's 1 is right here. Where's my pointer? Oh my god, I lost my pointer. Oh, it's right here. So my pointer. So this is the curve. There is a temperature. Critical temperature is here. You see, and we even have reduced volumes. Okay. 5. And our reduced volume is let's see what we have. A reduced volume. You have a 0.02. Okay, so now we're going to move up until we hit the graph, and let's see. Oh, until I hit the, oh, sorry. Okay, yeah, back in line. No, that's messed up. I just messed up. Sorry. Point is, you have to look for a value that is going to knock this curve right here, and it should knock it at a point somewhere here, which is going to give you a value of 0.806. And how do you read it? You straighten your line, it hits here, and then you look for the value that corresponds from here. So once you get the value that it's beyond 0.9, you have to redo it because it, just now you're doing something wrong. So we got a value as 0.86. That's the compressibility factor Z. And remember, the whole question was determine the specific volume. So after getting your compressibility factor Z, you relate it with this formula, which is specific volume over ideal specific volume. So once you correct like terms, the Z is over here, and you get a specific volume, which is equal to 0.86 multiplied by the ideal specific volume, which you calculated from part A. So if you failed part A, that means you're going to fail part B, and the whole question is going to be a mess, you know. So once you do your calculation, you get this value. Now remember, the question was like compare the values you get. So we're going to compare the values. How? By finding the percentage error. So the actual value was given as 0.02171, and we have gotten a calculated value as 0.2210999. Okay, 986, somewhere there. So the trick is you get the calculated value minus the actual value. You subtract them. So you already see this is 22 and this is 21. So this is bigger. You subtract and you find the percentage error, just like we did in the first place. And you're going to get 1.8% percentage error. And you make a conclusive statement since the percentage error is less than 2%, the compressibility chart is fit for use, you know. Or you could be like, the percentage error that accumulates, you know, from using the compressibility chart is way too less as opposed to the one that amounts from using the ideal Gauss equation, because in the ideal Gauss equation we got a percentage error of around um 21.24%. It's like you're doing total errors, total mess, which is quite different from here. We have a percentage of 1.8, so we are very correct. So more examples. Okay, problem one. So the question is a 0.0167 meter cube tank contains 1 kilogram of refrigerant 134A at 110 degrees Celsius. Determine the pressure of the refrigerant using the ideal gas equation of state. The generalized compressibility chart. Compare your results with the actual value of 1.6 megapascals. So the answers are right here, and we're going to go through the steps and we see whether we're going to get something related to these answers. One thing you have to notice immediately is that we're using the same refrigerant as before, and this should be quite easy. Okay, so there's the solution from the ideal gas state of equation of from the ideal gas equation of state. P, which is pressure, apart by the specific volume is equal to RT. So what are we finding? Determine the pressure. This time we want the pressure. So specific volume. Actually, one thing that I'm missing out, and it's not a good thing, is um, listing things that have been given in the question. Should I do it here? Yeah, I think even before you go anywhere, like here, you should. It's a good practice to first, volume of the tank. That's capital V is equal to 0.01677, and you put the units. Okay, okay. Now that's one mass, 1 kilogram of refrigerant mass is equal to 1 kg, and temperature T is equal to, oh sorry, is equal to 110 degrees Celsius. So we put the units. I've not activated my units, as you do this work. So, but it's a good practice before you answer a question in mathematics and physics and chemistry to first list down the quantities that have been given to you. It's easy to work with that. And they want pressure. You be like, question mark, okay? It's going to guide you. So now we can go ahead. But I should have done that before because now I've distorted my work. So I'm just going to go back. I was just showing you what you can do because I just distorted my work. Okay. Now I think we are good. Okay. So in the next video, I'll work on that. I'll make sure we derive, we dissect the question together, dissecting in the sense of you first extract whatever properties and its units that have been given, and you list what you have to find. In this case, we find pressure. So once we have the total volume, how do we know its total volume? I've said 0.0167 meters cubed tank, okay, as this volume tank contains. But there's another question will come. Our tank contains 4 liters of water, so that's not total volume. That's volume for the for that thing, okay, for the liquid. But now they say this volume tank, that means the total volume. So to get the specific volume, we get the total volume divided by its mass, by the mass, and we have 1 kilogram, which is this. Okay, so pressure from this ideal, we can divide and get 186 1.1 megapascals. But you see, obviously we know the units of pressure are megapascals. Okay, but how do we get there? Because we calculating, we're dividing meters meter cubed per kilogram with kelvins with the gas constant. How are we getting there really? So you might not need to derive the units in an exam, but You have to know where they come from. So I'm gonna help you through that. That's why I put units and I put a question mark. You know, you would just put megapascals and you find you're wrong because you see the answer is 1.861, not 186, 1861.1. So we're going to derive the units and we see how we get to this answer. So unit, so I put units derivation. So the units of multiplication of the gas constant and temperature is equal to kilojoules divided by kilogram Kelvin. So these are the units of the gas constant is kilojoules per kilogram per Kelvin. Okay. Now you're going to multiply by Kelvin. You're multiplying temperature with the gas constant. So the Kelvins are going to cancel out and you have kilojoules per kilogram. Okay. But now we're going to divide this with specific volume. Okay. So what do we have? We have this. I hope we are following each other. So pressure is equal to RT divided by specific volume. And we already know that the dimensions of RT is equal to kilojoules per kilogram. Okay, this is for the gas constant multiplied by temperature. And now we're going to divide it by specific volume. So, and when you're dividing, you take the reciprocal. So here is reciprocating to get mass cubed of a kilogram. The kilogram is going to cancel and you have kilojoules per meters cubed. That's taking us to the next step of joules. Joules is equal to force times distance. So joules is like the force is like the force that gives how do I even say that? How do I state that? Is the force that gives a body of 1 kilogram. No, 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 no. Okay, no, no. Just what you have to know is it is force times distance. The units of force is 1 Newton, and the units of distance is 1 meter. So joules is equal to one. So now you're going to substitute for the values of Newton. And we know that Newton is a force that gives a body a mass of 1 kilogram and acceleration of 1 meter per second squared. That's what we have here. It gives a mass of 1 kilogram, an acceleration of 1 meter per second squared. That's why we're substituting for the Newton. So we have distance is 1 meter. So once you multiply the two, you're going to get 1 kilogram meters squared per second squared. Okay, we good? Yes, we good. But remember, we have kilojoules per meter cubed. And we just, this is just for the joules. So we're going to substitute this here for the joules. So we have kilo into this which we got here multiplied by per meter cubed. Mm-hmm. And that gets us to, you know, there's 2 here and there's -3. So we have, this is going to reduce to a -1. So we get kilogram here per meter per second squared. So this is literally kilopascals. That's how we arrive to the kilopascals. How do I know it's a kilopascal? There's also a question. Once you go deep into the the derivation of the okay, I can do it for you. Pascals is the unit of pressure, and pressure is equal to force over area. So we already saw the units of force is kilogram meter per second squared. So now we're going to divide by area. What is area? Area is equal to, the units of area is meters squared. So once we put meters squared here, remember this is for the meters, so we're not considering it. So we have meters squared under the brackets. Now we cancel 1 meter and one of the powers. So we have a kilogram and second squared and a meter here. That's what we have here. Kilogram per meter per second squared. And that's a Pascal. So we have kilopascals. That means from our calculated value here, it's a megapascals, but it's rather kilopascals. So we have pressure is equal to 161, 100, okay, it's 1861.1 kilopascals. And the answer in the question is in megapascals, okay? It's and also like using the referency of the tables, property tables, you realize that pressure is given megapascals. So you, after calculating your values, it's one's decision to convert them into megapascals. So how do we convert? Is also a crucial part. So we have kilopascals. So you're going to multiply with, remember, we're trying to eliminate the kilo, the unit of the kilo, into a mega. So whatever you want, you will put it in such a way that it's going to divide. You see? So right here we're going to say 1 mega is equal to 1000 kilo. But instead of putting the equal signs, we divide, you see? So if it was like you were relating a centimeter with a meter, you'd be like 1 meter is equal to 100 centimeters. So if you wanted convert back into centimeters, you'd be like 100 centimeters is equal to 1 meter. But you don't put the equal signs, you just put a division sign, just like this. So it is 1 mega is equal to 1,000 kilo. Like mega is multiplying 1,000 with another 1,000, 6 zeros. So the kilo element, so the kilo is going to cancel, and you have your mega here. So once you divide here, 1, 2, 3, you get 1.8611 megapascals. And that's how we got our answer, which is very similar to what was given in the question. So they told us to compare our results, and from result comparison, we get the ideal pressure minus the actual pressure. This is the calculated pressure minus the actual pressure divided by the actual pressure. Multiplied by 100%, you get a percentage error of 16.31875%. So it will always be just like that. The result from the ideal gas equation is going to have a lot of percentage error. So now we go to part B using the compressibility chart. So from a previous example, we saw that to use the compressibility chart, the chart is such that we have the compressibility factor on the y-axis and the reduced properties on the x-axis. So to use the compressibility chart, you will have to find the reduced properties. And how do you find the reduced properties? You find the reduced properties by dividing that property with the critical property. And the critical property is given on table A1. In the previous example, I gave it to you. So let me see, did I bring it back? Oh no. Sorry, sorry. Yeah, but you should have your tables, you know. And from here you can check table A1 has the critical properties of refrigerant R134A. The reason why I didn't put the table again is because we're using the same refrigerant. In the previous example, we saw the steps on how to get the values. So it's right here. Critical temperature is equal to 374.2 Kelvin. Critical pressure is equal to 4059 megapascals, and critical volume is equal to 0.193 meters cubed per mole. In reduced properties, now you're going to divide and you get 1.0235 and 0.0841. The difference now for this question is here. Here comes the difference. Remember, in the previous example, we were looking for the specific volume, but now we are looking for the pressure. And this is crazy. We have been told to use the compressibility chart to find the pressure. And yet, to use the compressibility chart, you must have pressure. So that's quite absurd. Someone be like, so what are you saying? They're telling us to find the pressure using compressibility chart. If to use the chart, you must have reduced pressure. But to find reduced pressure, you must have calculated pressure. So what do? We're going to use something called iterations, like an assumption. So we already know for the refrigerant 134A, a moderate pressures, the compressibility factor is going to lie between 0.8 is going to be 0.8 is not equal to Z is not equal to 0.9. Where we should know that it's like a law, it's like a rule, for this question. And you state it, you'd be like by iterations, and then you put it. And you pick, you're going to pick the value of Z. Remember, if if we could find the reduced pressure, we would just get this value. We was going to just find it by tracing out a line until it meets the curve. But now we cannot have a reference reduced pressure, so we have to guess. So now you're going to pick this guys in between. And here we're going to pick 0.85, and from that you know that the compressibility factor is equal to PV divided by RT. So now you can find the pressure by dividing the compressibility factor with the gas constant, with the temperature, and the specific volume. And we already know that anything that results in here is going to be pascals. I'm sorry, this is a mistake. It shouldn't be here down. Can I sort that? Yes, let me see if I can claim that. Can I really? Yes, I can. Yes. Okay. And I'm gonna save. So the unit should be on top here. Does the effect might work? Should just be like copy and paste. Yes. Now that's correct. Okay. So we have this and kilopascals. Why are we putting kilopascals? Because we derived it already. We already know that it's gonna be kilopascals. Was it in the previous example or this example? I'm not quite sure. But within this video, we derived these units. So once you get these units, you want to convert them to megapascals because that's the standard unit. Okay, and how do we? We'd be like we multiply by what we want. It'd be like 1 mega is equal to 1,000 kilo, and the kilo is gonna cancel out, and we get 1.58194 megapascals. So they told us to compare our values with the before you go anywhere. After finding, remember we are using an assumption of z is equal to 0.85. So after getting this value of pressure, you have to check whether the assumed compressibility factor is actually it is the actual value, actual compressibility factor you would get if you knew if the reduced pressure was given. So how would you going to do that? You want to be like check. Be like reduced pressure is equal to actual pressure minus critical pressure, and you divide. This is the pressure. You use the pressure that you've gotten from the assumption, which is right here. You divide by the critical pressure, which we get from table 8.1. We went through how you get it, and we're going to get 0.39. Remember, reduced properties do not have units. So we have 0.39 as the reduced pressure. So we're going to go to the chart. Really, sorry, so we will have to go back to this. Okay, we have a pressure of 0.39. Where do we get 0.39? Let me see, 0.05 times 3 times 5 times 6 times 7 times 8, okay, times 7.5, 7.8. Yeah, so to use this table, I remember I told you you get the value of one column, one small box, which is 0.05. You multiply it by a given number until you get that value you're looking for. So once you multiply 0.05 multiplied by 7.8, you're going to get a value of 0.39, and that's what we're looking for. So that means you're going to go to the round of the number of boxes, which is 7.8, that is almost 8. So you want to count until you reach on the 8th box. Should I zoom out? Let me zoom out. I really don't like zooming out. It messes up my work. But let me zoom out, let me zoom out, let me zoom out. What do I do? Let me zoom out this. Sorry. Oh shit. Ooh. Okay. So this is box 1, 2, 3, 4, 5, 6, 7, 8. Let me bring my pencil. Bring my pencil. Sure, let me use purple. Okay. There's 1, 2, 3, 4, 5, 6, 7, 8. So somewhere here. Let's go up and see. Ooh. We're here, we're here. I'm shaky. I know I'm shaky. Huh. How's it? See? So we are meeting the line somewhere here. Sorry. Oh damn, what did I do? Oh yeah, we're good. So we pencil back here again. You have made the line there. So let's count. This is 1, 2, 3, 4, 5, 6. That's 0.86. Oh my god, we're so accurate. We are so accurate, aren't we? And we're so accurate. Like, we are so accurate because we assume the value of z would be 0.85, and indeed from what we've just done, we saw it's 8.8, 0.86, between 8.5 and 8.6. So we assume the correct value. That means this value of pressure we just calculated is correct. And we can put therefore pressure is equal to 1.582 megapascals. Is that what they have? Let's first check the question because they gave us the answers. Give us the answers. Is it? Oh my god, it's the one. 1.586 megapascals. Hey, okay, okay. This is a good one. See? So result comparison, you'll be like, get the percentage error, and the percentage error is equal to 1.12875, which is too small compared to 2%. The compressibility chart gives lesser error as opposed to the ideal Gauss equation. You can conclude like that as your conclusion. And yeah, I want to compile more worked up examples, you know, and questions, and we go through them together. So make sure you come around for more, more questions and more examples, and we go through this together. Okay, see ya.